Well, I bid you welcome. Got a lecture we need to do here that is somewhat kind of optional and still very good, very important. So let's do that real quick here. It's going to be mostly lecture. I've got a potential example problem we may or may not get to. Let's just kind of see how it goes. I apologize. I'm grabbing all this stuff. I should have been more ready, but here we are. I think I'm ready now. Let's get going. I'm going to share screen for us and let me move me up out of our way here. So again, we're talking about chapter 7 in the Chamberlain-Bowles 10th edition of Engineering Thermodynamics. And if you're reading along, which you should be, but that's a whole nother story about reading textbooks. For engineers, sometimes the reason I'm chuckling is sometimes engineers will just kind of get into this mode of, well, you just work the homework problems, work through example problems, and because as engineers, we solve problems, and so for us, we most of us really learn the material just simply by working through problems, and so it's easy sometimes to glaze over or gloss over the content of a textbook and dive right into those example problems and the homework problems and then working more problems. And that's very good for most people. That's certainly how I learn the material. Reading through the textbook is more of a challenge for me personally. But all that to say, I know some of you are still definitely very much textbook readers, and so you're reading through the textbook and you're like, Steve, there's this whole really cool section about entropy and the third law of thermodynamics that we haven't even talked about yet. Yes, I know that's why I kind of say it's kind of an optional topic. I normally try to work our way through as quickly as I can material about Gibbs equation and how do we use the second law quantitatively? How do we, because I want you to get armed with the tools you need to actually solve the homework problems. And I don't feel like we have to really have a good firm grasp on the third law to really work through the homework problems, but it's very important and it's good to talk about it, and that's where we are now. So let's work our way up to that. So again, if you're reading in the textbook, you'll see these sections talking about what is entropy. And we've mentioned it, we've kind of loosely defined it as chaos or unpredictability, and that's true. Um, I like this information here, this saying here. That's the words. Difficult to find, still a useful tool. Yes, very much so, right? And um, we talked about the phases of matter previously, right? What is entropy on and what it says behind my picture there is on the molecular level, right? What is entropy on the molecular level? As you move to the right here, you see that we're talking about different phases of matter. And in the solid phase, down here in the bottom, in the solid phase, the molecules are very predictable. It's easy to say, hey, that copper molecule is going to be in this location, in this crystal matrix at any given time because it's solid. The molecules are not moving relative to one another. As we move up in the energy gradients, as we move up to higher levels of energy and also higher levels of entropy, you get into the liquid phase. At the liquid phase, the molecules have enough energy they can move around relative to each other. They're no longer locked into fixed locations like we see in a solid crystalline structure, but they're still at a low enough energy level that they clump together, like the water in my bottle here. They're stuck to each other. They can't overcome the molecular forces that draw them together, and they form a clump. They form a liquid. Um, in the gaseous or the vapor phase, though, they have enough energy that they overcome the forces that want to hold them together in a liquid phase and way have overcome the forces that slow them down and draw them together into a crystalline solid phase. So again, as those molecules become more and more energetic, they become more and more chaotic, their motion now is becoming less and less predictable because they're no longer trapped or locked to each other. They can overcome the forces that attract those molecules together. And when we do that, They become more and more chaotic, more and more unpredictable. Unpredictable. Okay. So our good friend Rudolf Clauses, we've talked about him before. I've even shown you his picture. So again, you have somebody you can direct your ire to as you're working through these problems. Our good friend Rudolf Clauses, he came up with the idea that uh, he built on the work of Carnot, and he came up with this understanding that quantifying why a hot body is going to spontaneously lose heat to a colder body, and you really can't, without doing a lot of serious work, you're not going to be able to do anything other than that. So, and what we find is that means we're working within the confines of the laws of thermodynamics. We've talked about the zeroth law quite a while back, early in these lectures. The first law we've spent a lot of time throughout the entire sequence talking about the energy of the universe is constant. Energy must be conserved. Now we understand the second law is basically telling us entropy is always being generated. Right? And entropy is going to dictate how that energy can be transferred, how energy moves. So if we look at what entropy is in a quantitative sense, entropy, as we've said multiple times, is the measure of chaos. It's the measure of randomness, the measure of unpredictability. So I think we've talked previously about statistical thermodynamics, where for several hundred years there was massive studies into how do we actually quantify the energy of a molecule? How do we quantify the entropy of a molecule? We have the works of previous individuals that we can fall back on. We, in general, don't have to do that. We leave that to the physicists and the scientists, at least us as engineers. We don't a lot of times have to focus on that. A method, or one of the primary methods they're going to use, is this expression here, where they're using a quantity called the Boltzmann constant. I'm not going to know a whole lot about that. You're welcome to go look up what that is and what it represents. There's plenty of information out there. Times the natural log of a quantity we call the thermodynamic probability, P, lowercase p. Now, by the way, this K is not the specific heat ratio that we've been talking about previously. It's the same letter K, it's a different quantity. This is a constant describing phenomena in nature. The thermodynamic probability, P, that is our ability to predict exactly what a molecule is doing or an atom is doing and where it's going to be, exactly where it's at, XYZ location, exactly how it's moving, rotating, vibrating, and exactly what it's going to do in the next instant of time. If we can completely predict what it's doing, that's a thermodynamic probability of 100% ability to predict what a molecule is doing and where it's going to be. A zero is there's zero chance we can predict exactly what a molecule is going to be doing and where. So as the molecules become more and more chaotic, as they tend towards that gaseous phase, then our ability to predict what they're doing becomes less. And think about what the natural log of zero is, right? Let's look at the limits, like the limit of this entropy as P approaches zero or P approaches one. Think about what the natural log of zero is. Well, that's undefined. That's infinite, essentially, right? So if we have zero ability to predict what something is doing, it has infinite entropy. And if we have a 100% chance of predicting what something is doing, what is the natural log of one? What is the limit of this function as P approaches one? You get zero. Yeah, you get zero. It's zero. I said it out loud. I was like, wait, does that make sense? Yeah. Natural log of one is zero, meaning if I have a 100% chance I can predict what something's doing, that means it has no unpredictability. It has no chaos, no randomness. So a natural log of one means zero entropy. So here's what we know. If we've talked about before, if I take a substance like my water and I add heat to it, as I add heat to it, its temperature is going to increase. What does that mean? That means our ability to predict what the molecules are doing become less and less predictable. They become more and more chaotic. So as the temperature increases and in most substances, temperature and internal energy are heavily linked. As the temperature increases, the internal energy increases, and also the entropy increases. Okay. Now, um, so here's the third law. Okay? Here's the idea behind the third law. So as the temperature, or at the temperature of absolute zero, what does that mean? At absolute zero, we believe that is the point where all molecular motion stops. Okay? So what does that tell us? Well, if I have, move me back up out of the way here. If we have a purely crystalline substance, something that forms a true crystalline solid, many substances do this, right? If I have a pure crystalline solid substance, that substance at the temperature of absolute zero has an entropy of absolute zero. This is the third law of thermodynamics. Again, quotations without a source means that's coming directly from our textbook, Changle and Bowles, 10th edition, Engineering Thermodynamics. The entropy of a pure crystalline substance at absolute zero is, or yeah, at absolute zero temperature is zero entropy. Because if these molecules are locked into this crystalline structure and they're not vibrating or shaking or trying to rotate within that crystalline structure, they stop moving and they're trapped in this crystalline structure. So we know exactly where they are in X, Y, and Z, and we know exactly how they're moving within that XYZ crystalline grid. That's 100% chance we can predict what they're doing, which means zero entropy. Right? This is the third law of thermodynamics. Not something just like the zero law. It's not an equation that another law now we're going to have to figure out how do we apply to a problem. No, no, no. This is just a statement that we can't show or prove mathematically using the other two laws. So it has to stand as its own understanding statement, its own prevailing law, prevailing theory. So this is the third law of thermodynamics. And really all we have to do is kind of point to it and say, this is the thing, right? And we can talk a little bit about what that means for us. How does that help us? Well, at the end of the day, the first law, and if you think back to when we first started talking about the first law, first started talking about energy and, is this heat or is it work? And the first law really doesn't care, honestly. It just wants to know, are we increasing or decreasing energy? That's all the first law is revolves around. Are you adding energy? Are you decreasing energy? And how does that affect the energy change of our system? The second law, though, it is important whether we are dealing with heat or work, because these are two different energy transfer mechanisms and they affect the entropy of our system differently. So if I add heat to these molecules, then they're just going to start moving more chaotically. Heat is a chaotic energy transfer, as opposed to if I throw this, the current phrase is yeet. If I yeet this bottle, right, I'm doing work to it. I'm adding energy to it. But how is that impacting the molecules when I add energy to it in this way, when I do work to it? Well, what happens when I add work to it, I'm getting all the molecules to move together in a predictable fashion. I'm adding energy in such a way that it doesn't increase the entropy of the substance. I'm adding energy, but the molecules are still moving in a very predictable fashion. That is work. Work is when you add energy to a substance by applying a force to all the molecules in that substance, and that force causes all the molecules to begin moving in a predictable fashion, not an unpredictable fashion. That's the difference between work and heat. We say heat is, I'm saying here, heat is this low quality form of energy, where work is this very high quality form of energy, at least from an engineer's perspective. If all the molecules are moving in the same direction, I could probably use that movement then to drive something else, like a water wheel, like a paddle wheel, like a wind turbine. If all the molecules are moving in one direction, I can easily use that to harness and get predictable motion occurring, and that then I can use to generate a force, and I can use that force to do other work in some other quantity or some other system. Right? In my intro to engineering course, we talk about the difference between engines and motors. Engines being something that takes a thermal or chaotic form of energy and converts some of that energy into work, whereas a motor is something that takes um, motion, mechanical energy, and converts it into another form of mechanical energy. Okay. So that's a little bit about a little deeper look into what is entropy, a nice look into the third law of thermodynamics. And I just showed you here. I do have an example. I'm going to go ahead and record kind of setting this example problem up quickly. I'm not going to solve this out, but it's a nice, anyway, we'll pick up the next video from here. Okay. I'm going to stop recording.